All right, so this is the second hour of Physics 1A for May 5th. Yeah, Conan, that's pretty much right. Drag's based on velocity. High velocity is higher drag. Depends on surface area as well, so that's part of why when you're skydiving you want to make yourself large. And then terminal velocity is the maximum velocity the object will reach before the drag force starts to equate with the other forces, which is basically weight, right? So when your weight is equal to the drag force, you're moving at terminal speed. Because you found a balance between the rate at which you're falling and the force that it produces and your weight, which is the thing that's pulling you down. So it makes you feel weightless, which allows you to, move around in a way that's probably pretty fun and slightly unnatural. Okay. So just kind of summarizing a discussion that we had about drag just a second ago. Okay, so next thing we're going to do is we're going to relate the angular quantities that we just talked about, angular speed, to like linear speed. So, for example, if I have an object that's rotating, so again, let's use a circle. And let's say this is, let's say that we're talking about like a bicycle wheel, so we can relate this to something that we all kind of have some familiarity with. So I have a bicycle wheel right here. And let's say that it's rotating in a circle, so it's rotating this way. So it has an angular speed that goes like that, which would technically mean that its angular speed would be a vector coming out of the screen. And now let's say that we want to talk about the motion of like a point on the wheel. And at a point in time, we can say that this object, this point, can have a velocity, this point on the wheel, that we call its tangential velocity. And we need one other thing for this. We're also going to need to define what the radius of our wheel is here. So let's define the radius to be capital R. And the tangential velocity, we're going to use the symbol v sub t. So we basically like to relate vt, omega, and r to each other. All right. I think I probably already gave you this relationship when we were talking, because I think this came up last week when we were talking about circular motion. The relationship is basically that the tangential velocity is equal to the radius of the wheel multiplied by the angular speed. Okay, we can derive this. It's not very hard to derive because we can just relate the two to each other using the circumference of the circle. So, for example, we can say in one revolution, we know that the tangential velocity, because it's a linear speed, okay, is equal to the circumference of the circle, 2 pi r, divided by the time that it takes for it to go through one revolution, which we call the period. Just to remind you, t stands for period. And it means the time for one revolution. Right? So if that's the time for one revolution, then if I take 2 pi r divided by t, that gives me the tangential velocity. But the relationship between period and angular speed is that omega is equal to, it takes 2 pi radians in the period, which is t. So that means that, you end up getting that this is the same thing as omega multiplied by the radius. So that's the relationship. I think I actually did this derivation when we were going through one of the problems last time because it came up. So that's the connection then, that tangential velocity is equal to the radius of motion, so however far out you are, multiplied by angular speed. Now, when you look at something like a wheel like this, what you can say is that all parts of the wheel have the same angular speed. So this quantity is the same for all parts of the wheel. Okay? But tangential velocity is not the same for all parts because different pieces go through different angles. So for example, if I was to take a point right here on one of the spokes of the wheel and I was to consider what it's doing, it's going to have a smaller angular velocity because it has a smaller radius vector that goes out this way. Okay? But any point on the wheel, like let's say I pick this point right here and I look at what it does over one period, it's going to go around one revolution. If I pick another piece right here and I say, how far does this travel in terms of angles in one revolution, it's going to go around one time. So all the different pieces have the same angular speed. That's going to be important for some things we're going to do here in a second. But the tangential velocity of different points is going to be different. And the farther that you are out, the bigger it's going to be. So for example, if I take an object and I pick two different points that are exactly half as far as each other. So I have one point right here, and it has some tangential speed that I call, let's say, v2, and I have some point right here that has a tangential speed that I call v1, and I tell you that these distances here and here are the same, then I can tell you that if the object is rotating, that v2 is going to be equal to twice v1. All right? The farther you are out, the bigger that your speed's going to be, and the bigger your velocity is going to be. And that velocity is going to depend on how far away you are from the center R. Okay? Does that make sense? So this R, if it represents the radius of the object, this just represents the tangential velocity of some point on the rim. So really, maybe using capital R is bad. And really what I should just use here is just R, where R represents the distance from the axis to the point. Where you want to find the tangential speed. Okay? Now, the next thing we can do, which is pretty easy, is to relate the distance the object travels along a path. So, if an object moves between these 2 points, for example, we've defined that there's an angle right here that we call delta theta, right? And, God, that looks awful. Drawing the little spokes here makes this diagram look awful. Anyway, if this is delta theta, then we can define this distance on the outer rim right here to be s. So that's the other relationship. This one you all pretty much already usually know. S equal to r delta theta, right? This is the relationship for as long as you measure the angle in radians, the arc length is related to the radius times the angle. And then the final one that we can get is going to come from this one right here. So if we know that the tangential velocity is equal to the radius times omega, we can just take this and take the derivative of it. And on the left-hand side, what we'll get is the tangential acceleration. And on the right-hand side, what we'll get is the radius is going to be a constant. So we just take the derivative of omega, and d omega dt is alpha, so you get r times alpha. Okay. Now there's one other quantity that we want to talk about, and that's the radial acceleration, or the centripetal acceleration. And in the previous chapter, we said that radial acceleration, or centripetal acceleration, was given by v squared divided by radius, right? And again, this is another derivation that came up last time, so I think we did it last time, but just to go through it again. What we mean when we talk about tangential acceleration, when we talk about radial acceleration, we mean tangential velocity. So if we plug that in here, we're going to get r squared omega squared divided by r, which is equal to r times omega squared. So then that's the other piece of this. Radial acceleration is going to be given by r omega squared. So keep in mind, these are not the same thing. So tangential acceleration is going to be the rate at which the object is speeding up tangentially, and radial acceleration is going to be the rate at which it's turning, basically. So what I say is that tangential acceleration represents the rate at which the object is speeding up or slowing down. And I call this one the rate of turning, because it's radial. And these two are right angles to each other, right? So if I have a circle, let's draw another circle down here. then, and I have an object that's traveling around this circle, so it travels from here to here, for example, then I can define the tangential acceleration to be this way, and I can define the radial acceleration to be this way. And they will always be at right angles to each other. Okay, so these three ideas are going to be pretty useful to us, and this one's always useful as well. So that's the relation of angular quantities to linear quantities. Anyone have any questions about those definitions? Okay, so the next thing to talk about is energy. Didn't leave nearly enough room here. Okay. So when I have an object that's rotating, we've learned that it has quantities like angular speed and angular acceleration. So we'd like to take those quantities and relate them to energy. So we've learned about two types of energy in this class. We've learned about potential energy and kinetic energy. I think that without a doubt, if you look at an object that's spinning, you would all agree, like you look at a tire that's rolling in a car, or you look at the wheel of a bicycle, or you watch a child play like on a merry-go-round in a park or something like that that's going around in a circle. There's no doubt that there's energy, and we just like to be able to quantify how much there is, okay? So again, we'll take an object that's rotating, and let's draw a line to represent a radius vector right here. So we have this object. It is rotating with some angular speed. As we said before, if I tell you how I have a circular object and it has an angular speed omega, actually it doesn't even have to be circular, okay? Anything that rotates is going to have the same angular speed for all of its parts, okay? So I have some kind of disk and it's rotating, and I want to describe the energy associated with it. So our definition of kinetic energy up till now has always been just kinetic energy is just 1/2 mass times velocity squared. But one thing that we kind of have left out of this is that this velocity that we're describing right here has to be linear velocity, and specifically, it has to be the velocity of the center of mass of the object. Okay? This has to be the velocity of the center of mass of the object, so I'll put VCM right here. If I have an object like this, whose center of mass is right where the rotational point is right here, so if the center of mass is right in the center and it's rotating, so it's just rotating, okay? Imagine like take a bike, turn it upside down, the wheel is just rotating, okay? Then the velocity of the center of mass is 0. So its kinetic energy would then just be 0, right? But if we start to look at all the different pieces of our object here, so we break our object up into different pieces. So this is going to be one piece. It's going to have a tangential velocity vector that's going to go this way, that I'm going to call v1t. And I'm going to say that what we're going to do is we're going to take our uniform object. So let's say this is a uniform disk, like a wooden disk or something like this. And we're going to basically say, suppose that we break up our disk into a bunch of little tiny parts. So this piece that we're going to say that this piece is moving with the speed of v1t, okay? And then I pick another piece, maybe pick a different color, and I draw another vector, or another radii vector right here. And on this little line right here, I'm going to draw another piece. So we're going to call this one m2, and we're going to say it's going to have a velocity vector that's going to go this way. And again, this is going to be the tangential velocity, so I'm going to call it v2t. And then I'll draw one more. So come down here. And on this little line, I'm going to draw another vector. Not vector. Yeah, a vector. We'll say this is going to have a piece. This piece is going to have a mass that we call m3. Its velocity vector is going to go this way. We'll call that one v3t. And these should all be right angles, but they're not exactly right angles. We need some other pieces of information for this too, though. I'm going to call the distance between the center of the object and mass 1 to be r sub 1. I'm going to call the distance to m2 to be r sub 2. And I'm going to call the distance to m3 to be r sub 3. Okay. Now, these are all technically vectors, but I don't think we really need to define them as vectors in this case for what we're going to do. Okay. The other piece of information that we're going to need that we just derived is the relationship between tangential velocity and angular speed. So that is the v tangential is equal to omega multiplied by r, or r, I usually write it as r omega, I guess. Okay. So let's put these all together. So even though the kinetic energy that's defined right here is a type, this is like translational kinetic energy. And it says it's the velocity of the center of mass, and the center of mass of this object isn't moving. What I could say is that, what if I looked at this object and I broke it up into all these different pieces like we have right here? Certainly, each individual piece is going to have kinetic energy, right? In fact, I can say that the kinetic energy of this little piece right here that we're calling m1 would be 1/2 times m1 multiplied by its tangential speed squared, right? I could say the same thing for the second object, that it has a kinetic energy that would be equal to 1/2, these are two different things, 1/2 mass times its velocity squared. So it's m2, and then it's v2 tangential squared. And I could go through my entire object, and I could pick out every single piece, and for every single piece that I pick out, I can write this exact same expression down until I can say that the total kinetic energy would be equal to basically the sum over, well, let's not write it as a sum yet. It's going to be something like this. It's going to be 1/2, I'll pull it out to the front, m1 v1t squared plus m2 v2t squared plus m3 v3t squared plus, and then we have to do this, basically, if I want to get the total kinetic energy, I need to sum this over every single piece of the object. So effectively what I have to do is to break this object up into probably a very, very large number of pieces, and then I have to write this entire expression down like this, basically, to include the entire object. Okay? Okay. So, do I have any questions about what I'm doing? Does this make sense so far? Does it seem reasonable that if I want to find the kinetic energy of the entire thing, that I'm going to have to find the kinetic energy of every single piece of it and basically just add them all up together? It's the only thing we know how to do, because this is our definition of kinetic energy. And this refers to a whole object, and the center of mass just isn't moving. So this isn't going to work. We need a new definition of kinetic energy for the object that's rotating. Yeah, that's right, Andrew. And you can think of this as basically saying, like, you know, take a circle and then just superimpose a grid over it, right? Like this. And then every single grid piece is an object. And they all have rotational motion. And yeah, and then if you want to find a really definite answer, you would just make the grid pieces as small as you possibly can. We're not integrating, no. We're not actually integrating. We are adding up a whole bunch of things, which technically is what integration is. So in that sense, I think that maybe that's what you mean. Then that's fine. Okay, so this is obviously a pretty exhaustive process. It could take a long time to define what the velocity of each of these are. But the thing we have going for us is this. We know that every one of these tangential velocity vectors is just equal to its own radial position multiplied by angular speed. So let's plug that into our equation here. So we're going to have m1 times v1t squared is now going to become r1 multiplied by omega. The good thing is that there's no omega 1. Remember that the entire object has the same angular speed. That is really important for this. The whole object, no matter if I pick a piece here or here or here, it doesn't really matter. Every single piece of the object has exactly the same angular speed. So that's what I'm going to get for v1t, and I just go through and do the same thing for each of these. V2t will be R2 times omega, and V3t is going to be R3 times omega. Well, remember, R3 is this distance, R1 is this distance, R2 is this distance. That's squared. Oh, we need to keep the sum going. And now we can factor out the omegas, because there's an omega squared in every single term. So we end up getting m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus ... all multiplied by omega squared, because every single term is going to have that same omega squared inside of it. And then we can now write this little piece right here as a sum. And the sum we're going to write is going to be the sum over m sub I r sub I squared from I equal to 1 up to just how many ever pieces we happen to have broken it into. If we broke it into 4 pieces, it'd be I equals 1 to 4. If we broke it into 100 pieces, it'd be I equals 1 to 100. And that entire sum is multiplied by omega squared. And this is going to end up being, I called it K total. It is the total kinetic energy of this particular object, but I'm going to call it K rotational, so K rot. We'll put K rotation. So this is going to define the rotational kinetic energy of my object, this expression right here, okay? The problem is that when you look at this expression here, that is seemingly a hard calculation to do. But what we can do is we can give it a name. We're going to call it I. And this is going to be the much simpler version of rotational kinetic energy for us. And so then I then is, since it's a uniform disk, aren't all the m equal to each other? Maybe, in this case Conan, but we'd like to have this be generalized to where we can apply it to any object, even if it's not uniformly distributed mass. You know what I mean? So I'm not just going to make all the m's equal to each other. Alright, so I is defined then as the sum over I equal to 1 up to the number of objects that you have in your system, multiplied by m sub I r sub I whole squared, and this quantity is what we call moment of inertia. Or there's other names for it. Other textbooks might use rotational inertia. I actually like this name a lot better. Although, for 40 years of my life, I've always used moment of inertia. Just recently, when I taught some other courses, I like the word rotational inertia. Or there's another name for it, which is kind of not very good, but it's also pretty applicable, which is rotational mass. Because this is effectively the analog of mass for rotational motion, okay? Moment of inertia, okay? And this is where it shows up. So to make this formula look a little bit better, I'll just put K rot for rotation and say that this is 1/2 the moment of inertia multiplied by omega squared. So what is this? So moment of inertia, or rotational mass, is an expression of how hard it is to spin, twist, shake, no, just spin or twist. It's how difficult it is to rotate an object, basically. It's about the resistance that the object has to rotation. That's what it represents, okay? So I'll write that down. So moment of inertia I represents how hard it is to rotate, twist, spin object. Okay. And the value of the moment of inertia depends on the axis that it's rotating about, okay? So this is not a quantity that's the same for even one object could have multiple different moments of inertia, okay? And it basically depends on, I'll just say right here, the value is dependent on which axis you're rotating it about. Wouldn't which point and axis be better to describe it? I don't understand your question. Can you say more? While he's writing that, do you all have in front of you, almost certainly, you all have like a pencil or a pen or something in front of you, right? Hopefully. All right, so yeah, that's my point, Conan. Exactly. That's what I just said. Rotating a cylinder from the end is going to have a different eye if it's on the middle for the same axis. Yeah, we're getting there. Just bear with me. Okay, so here's what I want you all to try. Find like the longest pencil or pen that you have. Okay, so don't use one that's really short. Like I think my stylus is probably too short, but it should still work. Okay, so here's what I want you to try to do. So basically, in whatever way you want to, hold the pen or pencil kind of between your fingers like this, so that you're holding it right at the center. And I think the easiest way to do this is just hold it between your index finger and your middle finger like this. And basically just do this, like try to wiggle it back and forth. I don't know if you can tell what I'm doing. Maybe I'm doing it too fast. But all you're doing is basically just you're trying to wiggle it back and forth like this, right? Kind of, we're not really like rotating it like in a full circle. We could do that, but I think it's hard to figure out what's going on here if you do that. Just kind of try to rotate it like this, basically, right? And try to keep your hand in the middle as much as you can. Get a feel for how difficult that is. It's obviously not difficult, right? It's not like lifting a 50-pound bag or something like that. It's not hard, but just get a feeling for the difficulty with which that takes. And then take your fingers and go to the very end, like this. You can either hold it vertically or upside down like this. Doesn't really matter. And then do the exact same thing. And then you all tell me, which one is it easier to rotate about? Is it easier to rotate about the middle, or is it easier to rotate about the end? About the middle, okay. Yeah. So, what we would say then is, because it's easier to rotate about the middle, rotating it about the middle, it's going to have a smaller moment of inertia than it is when you rotate it about the end. This is a larger moment of inertia, okay? And in general, it's because of the way that it's defined. The farther away the masses are, the more that they're going to contribute to this calculation. Okay, so when I rotate it about the middle, basically the farthest distance of any of the masses is half the size of the pen, right? That's the farthest point about which we'd be doing some kind of calculation. But we can double that distance by trying to rotate it about the end like this. Because now it's the full length of the pen. Like, some of the mass is really far away, basically, right? And the longer that this object gets, so if you happen to have a meter stick in your house, if you happen to have like a long pole or something like this, do the same thing. Like, go grab a really long pole, hold it about the center, and try the same thing. And then take the pole, if it's long enough, and grab it at the end and try to do the same thing. It'll be much, much, much harder. The effect increases with length because, and it doesn't do so in a linear way, it increases with length in a squared way, right? So if you double if I were to take a pen that was twice as big, the moment of inertia would be 4 times as big, right? Does that make sense? Because it's distance squared that shows up in this calculation right here, okay? So do I need to write all that stuff down? Or, I mean, we're gonna do some calculations and we'll look at some of these solutions and stuff like that, but it is easier to rotate an object about a point that is kind of more balanced than it is to rotate it about this right here. Now, there are other ways that I can rotate this pen, right? Can anyone tell me what's another way that I could rotate the pen that would be even easier, that it might have an even smaller mode of inertia about that axis? around its center, right? Like this, if you take your hands and try to basically just roll it between your hands like this as if you were, I don't know, rolling out pizza dough or something. This is really easy. There's almost no resistance to rotation when you do this, right? Moment of inertia is about resistance to rotation, right? And that resistance originates because objects have mass and mass has inertia. Inertia means that things don't want to move, right? Things want to stay still. Or once they start moving, they want to keep moving. But so the lowest moment of inertia for this pencil would be rotating it like this. There's almost no resistance to me doing this, right? There's, again, very little resistance to doing this, but there is some resistance that you feel. And there's even more resistance that you feel here too, right? So smallest moment of inertia is to rotate it like this. Next smallest would be to rotate it about its center. And then the very largest would be to try to rotate it like this. Does that all make sense to everyone? About like what moment of inertia is? And does anyone have any questions? Okay, so we have this definition. 1/2 I omega squared. We're going to do a calculation of I. But I do want to pull this one thing up from your textbook. You can find this all over the internet if you want to, if you Google moments of inertia. Oh, we were looking at other things, so I got a little bit lost here. Right here. There is I mean, most of you have probably already taken physics 2A, so you probably already knew this, but almost all physics textbooks have a little chart like this. What this chart is, it gives you the moment of inertia for various bodies based on their dimensions. So for the example that we were just using, the object that is a kind of a thin rod, we're going to refer to things like pins as being like thin rods, or this is a slender rod. If the axis is through its center, so that was when we were trying to rotate it like this, the moment of inertia is about 1/12 times ml squared. If you try to rotate it about its end, though, the moment of inertia is 1/3 ml squared. What that would mean in terms of the little kind of like demo that we just did would be that it is about 4 times as easy to do this as it is to do this. Right? 4 times, because this is a 12th and this is a 1/3. And I know fractions like can be kind of hard, but that means that this quantity is 1/4 the size of this quantity, right? Do you agree with that statement? Is it actually 4 times as hard to rotate something like this compared to like this? I don't know. It's hard. It's really hard to tell, right? And we're not good at figuring out things that are 4 times as hard, especially when it's like if I lift an object that's 10 pounds, then I lift another object that's 40 pounds, you might have a pretty good sense that it's 4 times as heavy. Although if someone didn't tell you that it was 40 pounds and 10 pounds, you probably couldn't exactly figure that out. You just know it was heavier, and you might know it's a little more than twice as heavy or something like that. So it's a similar situation right here. It's not obvious to you when you're doing this that this is 4 times as easy as this, right? But that's what the point of physics is, right? It gives us it allows us to quantify exactly how that works. Okay. Yeah. Right, Conan, exactly. In fact, before even looking at this equation, and before, I mean, I know what the answers are and stuff like that. I know that this is going to be a 12 and this is going to be a 1/3. But the reasoning that I gave was similar to what you said, Conan, which is you just look at this equation and you say, oh, well, this is half the length and this is the full length. So I know before even doing a calculation that because it shows up as r squared here, it's going to have to be a 4 times factor, like you say. That's a good point, exactly. Okay, so there's other moments of inertia, obviously, that are written here. There's a rectangular plate through its center. It has this moment of inertia. There's a rectangular plate along its edge. It has this moment of inertia. And then hollow cylinder, solid cylinder, thin-walled cylinder. These two are the ones you're going to see show up the most in your problems, are solid cylinders and thin-walled cylinders. So solid cylinder has a moment of inertia of 1/2 mr squared. We're going to use this in the next problem, well, not the next problem, but one of the problems we do today. And then a thin-walled cylinder has a moment of inertia that is twice as big, this hoop right here. Very common physics demo is to take a solid cylinder and a hollow cylinder and roll them down from the top of a ramp and have you all predict which one gets to the bottom first. And then finally, we have the solid sphere and then the thin-walled hollow sphere. So this last one is like a tennis ball where it's hollow on the inside. And this one is like a bowling ball that's solid throughout. Okay, so useful table of moments of inertia. The video that I linked basically goes through how to calculate some of these. Unfortunately, I linked the same video twice, and the first video that I linked actually had most of what we did so far today, so I apologize if you were confused when you were watching that video or if you watched it at all. But yeah, so sorry about that. Anyway, so here we are, moment of inertia, and now we want to do a few different problems that we can solve with this. The first one we're going to do is this one right here, and then we'll do these other two afterwards. So this is the first one. Let me just click, shift these off the page, and let's try to solve this problem here. Okay, so this is about calculating moments of inertia for two different rotation axes. So it says, a machine part consists of 3 discs linked by lightweight struts. What is this body's moment of inertia about axis 1 through the center of disc A? So here's our discs down here. We have A, B, and C. So we're going to find the moment of inertia through this axis. Let me just check the time real quick. Okay. We started at 3:25, right? So if we're going to take another break, we'll probably do this problem and then take a break. All right, so first we want to find the moment of inertia through this axis. And then it says, what is the moment of inertia about axis 2 through the centers of discs B and C? And then what is the body's kinetic energy if it rotates about axis 1 with angular speed, omega? Okay, so let's rewrite our definition of what moment of inertia is. Oh, and I didn't say this, but I should have. The r sub I in this equation represents the shortest perpendicular distance to the axis of rotation. Okay, that's what the r represents. This is a little bit redundant because shortest distance will automatically be perpendicular and the perpendicular distance will automatically be shortest, but I don't think it hurts to say both of them. All right, so here's our object. We have a mass A of 0.3 kilograms, a mass C of 0.2, and a mass B of 0.1. And these objects are connected by rods, but I believe the rods are all lightweight. So we're going to ignore the weight of each of these rods right here compared to the masses of these objects. So the first axis we want to do is through A. So for part A, we'll call that axis I sub A and say that it's going to be equal to, we have to sum over every piece mass times its distance. So let's start off with MA. So it'll be MA times RA squared plus MB times RB squared plus MC times RC squared. And we just need to go through and figure out what each of these are. So MA is 0.3 kilograms. R sub A is going to be the shortest perpendicular distance to the axis. In this case, the axis is A. So what is the distance going to be in this case? 0. Yep. It's on the axis, so we put a 0 right here. Okay. Next, we have MB RB squared. So we have mass B, which is and now we need to multiply by the shortest perpendicular distance. Now in this case, the axis is going into the screen, which means that what distance should I use? Should I use 0.4 meters? Should I use 0.5 meters? Yep, 0.5 is the right answer. So this is going to be times 0.5 meters, and we're going to square it. Because if the axis is coming out of the screen, then this 0.5 meters is also perpendicular to that axis, right? Okay. Plus M sub C is 0.2 kilograms. Multiplied by R sub C, which is going to be the distance from this to the axis, which is 0.4. And then that's squared. All of that's going to give us our answer for the moment of inertia. It's going to be in the right units. The units for moment of inertia are going to be kilogram meter squared. So let's just use the scientific calculator for this. Minimize this. Not that. Oh, it won't let me. I have to go out of full screen mode, right? Okay. So, all right. So that's the calculation we want to do. So it's 0.3 times 0 plus 0.1 times 0.5 times 0.5 plus 0.2 times 0.4 times 0.4. So 0.057. Sometimes these will be written in like kilogram centimeters squared or gram centimeters squared, depending on, yeah. Actually, there's certain things when you buy them, you can actually see what their moment of inertia is written on the packaging. Like a tennis racket. If you go buy a tennis racket, not all of them, depends on what company sells them, but some of them will actually have written on the packaging what the moment of inertia of the racket is. Because, you know, it's actually related to how much energy you can give to a tennis ball, or how much momentum you can give to a tennis ball, because or just, you know, depending on how fast you can rotate it, but also once it's rotating, how much inertia it has. Okay, part B. Where's draw? Let's do a different color. So for part B, we want to find what is the mode of inertia through axis 2 about through the centers B and C. So this is axis 2. I'm going to call it IBC. Okay. So this one's going to be equal to, again, mass of A times RA squared plus mass of B times, I'm using the same symbol, but it doesn't mean the same thing, RB squared plus MC times RC squared. Okay, so axis is through BC. That means the object is rotating around like this. What is the RA going to be? Yeah, 0.4. So we don't want the distance from here to here, because that's not a perpendicular distance, right? This is a perpendicular distance from here to here, so 0.4 is right. And then MB, what radius am I going to use for RB? 0 plus MC, also 0. Both of these are on the axis, so we don't need to do anything. So this is our entire equation right here. 0.3 times 0.4 times 0.4. So we get 0.048 kilogram meters squared. So what does this mean? Which of these two axes would it be easier to rotate the system about? BC, exactly. And that kind of makes sense because you're almost eliminating the inertias of these objects by putting them on axis right here. All right. We're also kind of neglecting the fact that these objects are disks, and technically those disks would have a contribution to the moment of inertia, but we're kind of assuming that the size of these disks is really small relative to these distances. I mean, half a meter is really far, right? 0.4 meters is really far. Okay, so that's IBC. Part C says, what is the body's kinetic energy if it rotates about axis 1 with an angular speed of 4 radians per second? So for part C, this is very easy calculation, because now that we know what the moment of inertia is, to find the kinetic energy, we just need 1/2 I omega squared. I'm just going to go back here real quick and point out something. I think something that sometimes people get confused by is this half that shows up right here. Maybe not so much in this problem. It's going to come up in another problem. Actually, I'm getting ahead of myself. Because the thing is that sometimes the I has a half in it. Specifically this one. 1/2 mr squared. So don't drop 1/2. That's what I'm trying to say. It'll come to the next problem. Okay, so that's what we get. 1/2 I times omega squared to find the kinetic energy. We wanted to use axis A, I think it said, right? Axis 1, which is going through here. So I sub A was 0.057. and we're multiplying that by omega, which is 4. Okay. So 0.456. And that would be the kinetic energy of rotation for the system. Any questions? So let's take a break. So we started a little late today, so we're going to do a shorter break this time. We're going to break until 4:20 p.m. So it's a 5-minute break. And then the last hour of the class will only be like a little bit short, it'll be 40 minutes.